Okay, welcome to the makeup lecture for the course. This lecture will be about just one simple problem, which is an application of the divide and conquer paradigm, and that's this problem of median finding. Okay, so just to recap, so divide and conquer is a very general paradigm of which we saw multiple examples in class. So you've got a problem instance, and so you have this large instance. You break it up into smaller sub instances. That's called the divide step, and you solve these sub problems. And often these problems are solved recursively, which means that they get further divided and so on. Okay. And so now you take the solutions to these individual subproblems and you combine them all to a solution to the full instance. Okay. So this step is called the combine or the conquer step. And so this is what we said is usually the tricky part. Okay. All right. So this is a general paradigm. Let's now see how it applies to kind of a non-standard situation. Okay. So the problem is the following. It's what is called the selection problem, or you can also phrase it as median finding. So you are given an array of let's say integers, and assume that they are all distinct for now. Okay. So it doesn't really matter, but assume that they're all distinct integers. Okay, and the key point is that A is not sorted. Okay, so entries of A are arbitrary, and now the goal is to find the n by 2th smallest element. Okay, so such an element is called the median, in case you don't know. So the n by 2th smallest element is called the median. Okay, now the goal is so that's the median finding problem. A slightly more general problem is what is called the selection problem. So here you are given an additional parameter k, and the goal is to find the kth smallest element of this array A. Okay, that's so this is what's called selection problem. Note that for both of these problems, an easy solution, which is kind of a baseline, is you first sort the array, and then you can basically read off the answers. Right? Like after you've sorted it, the median is just the n by 2th element of the sorted array by definition. Okay, and so the easy baseline is sorting, which takes time of n log n. Okay, now the question is, can we do better than this? Right. So in particular, you can ask, for example, if you can find the median in time of n. Right. Like note that you can find certain statistics, like you can find the, the the mean in linear time. Right. You just average all the numbers, and you can find things like the max and the min in time of n. So you might ask, okay, can I find the median and also in time of n? Okay, so it's a natural question. Okay. And of course, you cannot also beat O of n because just reading in the array takes time O of n. Okay. So in some sense, we want like the best possible algorithm for this problem. Okay. Now you might be thinking, all right, so you're given this array, you want the n by 2 smallest element. Where does divide and conquer fit in? Right? Because if you break this array up, then medians of these sub arrays probably have nothing to do with the median of the whole one. Okay, so let's see how divide and conquer applies. Okay, but this is the problem. Okay, and so the main thing so the main idea behind this solution turns out to be this idea of an approximate median. Okay, so what is this approximate median? Okay, so let's go into that. So let me first define the notion of an approximate median. So if I have an array, okay, and of integers, let's just write them as a0, a1, so on. Right? So an approximate median is a number that's roughly in the middle of the sorted version of A. Okay. So if I were to sort this and I get an array b0, b1, bn minus 1, then an element that's roughly in the middle of this array, which is formally I want at least n by 4 numbers to the left and at least n by 4 numbers to the right. Okay, so overall there are n numbers, so I'm looking at the middle n by 2 portion of the sorted array. Okay, now any number over here, I will call that an approximate median. Okay, so any of the numbers in the array, so okay, I also want x to be in the array. Number x belonging to the array is an almost median if there are at least n by 4 elements to the left of it and n by 4 elements bigger than it. Okay. So in other words, it's like one of the middle n over 2 elements. Now, so now the key assumption, which will be the starting point for this algorithm, is suppose you are given an oracle, okay, which given any array can give you an approximate median. Okay. Note that there are lots of approximate medians, right? So any of these n by 2 numbers is an approximate median. I'm saying that there is an oracle that gives you one of these things. Okay. So, so suppose you have an oracle of this kind. Okay. I would like to claim that the existence of such an oracle leads to a good divide and conquer algorithm. Okay. So let's see why that is true. Okay. So right? So the algorithm is now quite simple. Okay, so you start with the array A, okay, and you find an approximate median, and let's say it is some x which is equal to a of I. Okay. Now, so what does the picture look like? So you have this array A, which is unsorted, and x equals a of I. This, let's say, is an approximate median, which means that there are n by 4 elements in the array that are smaller than x and n by 4 elements that are larger than x. Okay. So now let's say I do something analogous to what quicksort does, right? Which is I partition this array A into two chunks. Let's call them B and C. B is everything that is set of all A of j such that a of j is less than or equal to x, and c is the same thing but more than. Okay, and by the definition of the almost median, both of by definition of an approximate median, size of b is bigger than equal to n by 4 and size of c is also bigger than equal. Okay, so that's what you've got. All right, so how does this help us? Right, so you've now taken, using X as a pivot, if you will, you've broken up A into two subarrays. One is B and the other is C. Both are reasonably large. Okay, this contains all numbers less than or equal to X, and this contains all numbers bigger than X. Now, the key thing is, let's say I'm trying to solve the selection problem. Okay, so actually one thing I forgot to mention is that I will throughout be talking about solving the selection problem, because I mean that's actually the harder problem, right? Like if the selection problem asks you to find the kth smallest element, if I set k equals n by 2, I get back the median. Okay, so I will always talk about the selection problem, right? So how does this, so now getting back to this arrays B and C. Okay, so I formed these arrays B and C. So now I claim that this leads to a divide and conquer algorithm, and it's not very hard to see why. Okay, because let's say my k is this given parameter, and suppose size of b happen to be less than k. Okay, so what does that mean? Right, so it means that size of b is something that is small, and it means that the kth smallest element in the array must be more than or equal to x. Right, because must be actually strictly more than x, because B contained all the elements in A that were smaller than or equal to x. Okay? And there were fewer than k of those. Okay? Which means that the kth smallest element of the array must be actually strictly bigger than x. Okay? And so let me consider two cases. K. Okay. So in this case, we claim that see that kth smallest element of A is exactly equal to the k minus smallest element of C. Okay, so this is array C. Okay, and why k minus size of B? Right. So imagine the size of B is let's say it's exactly n by 4. Okay, and so size of B is exactly n by 4, and let's say k is like n by 2. Okay. So then the n by 2 at smallest element is you remove these guys that you know were less than or equal to x. Okay. And among the remaining, you want the n by 4th smallest. Okay, so that's why it is k minus bth. Okay, so think about this for a little while if this is not clear to you. Okay, so that's what you get over here. Okay. And the second case is again very similar, right? So the case 2 is that if size of B is actually more than or equal to k. Okay? So let's say there are more than or equal to k elements that are less than equal to x. Okay, so in this case, okay, so what would the kth smallest element of B of A be, right? So if you think about it, A is if you were to imagine like A being sorted, then there's all the elements of B that show up on the left, and then there is X, and then there's all the elements of C, right? And by our definition, X also belongs to B. Okay. Now this subarray we said has size at least k. Okay, so this is an hypothetical, this is an imaginary sorted version of A. Okay, so here we know that there's the elements of B that show up over here. So remember, B is also not sorted, right? So B is just the collection of elements, right? So it's the elements of B but in sorted order, and X would appear at the end of this. Okay. Now, right. So and now we know that there are more than k of them. So if I want the kth smallest element of A, then it's exactly equal to the kth smallest element of B. Okay. So in this case, A is exactly equal to kth smallest element of B. Okay. So now, if you think about it, lo and behold, we have a divide and conquer algorithm, right? So this is exactly a recursive step, right? So it's saying that if size of B is less than or equal to k, then you do this. Otherwise, you look at the kth smallest element of B. Now, B and C are both arrays that are strictly smaller than A itself. Okay, so that's what we will see here. Okay, so we know that size of A and size of B are both bigger than or equal to n by 4. That also means that size of A and size of B are both less than or equal to 3n by 4. Why is that? Because if you know that a plus b is exactly equal to n, okay, and we know that b is at least n by 4, and that gives that a is less than or equal to 3n by 4. Likewise, we know that a is at most n by is bigger than or equal to 3n by 4. Therefore, b is at most 3n by 4. Okay, so that's why this implies this. Okay, so, sorry, these should be b and c. Okay, so that's what we have. And what this means is that both of these subarrays are actually much smaller than A itself, than the entire A, which means that in the recursive step, the size of the array is actually decreasing. Okay, so that's what we'll see now. Okay, so before we go there, so let me recall the algorithm. So it's a simple divide and conquer algorithm that we have at this point. Okay, so it's simply, I just wrote this out. Okay, so the procedures is called select, and A is the array that you're given, and K is this thing. I am assuming that there is an oracle called approximate. Okay, how this oracle is implemented will be the subject of the next couple of videos. Okay, but for now, assume that there is some oracle that tells you, given an array, it gives you a number x, which is an approximate median. Okay, once you have such a number x, I can partition A into B and C. Okay, so elements of A that are less than x. Okay, so I do this, and if k is smaller than b, then I do select on b. If k is bigger than b, I do select on. Okay, so I hope I didn't get these things wrong, but I've already explained before, so you get the picture. Okay, all right. So what's the running time of this? Right. So that's the next question that we want to answer. Okay. So the running time is there's only one method to do this. So we said that let's define a function. We'll call it t of n. It's the runtime on an array of length n. Okay. So when you pass an array a of length n, let t of n be the running time. And how does this procedure work? Right. So you run approximate median. Let's say so this takes some time. Okay. For now, we don't know what it is, right? So let's denote it by some f of n. Okay. So this is the amount of time that approximate median takes. Okay. And so you've got B and C. For the forming of B and C, this takes O of n time. And then there is some case analysis, and you either go into B or you go into C. But we just observed that both B and C, so we observed that size of B and size of C are both less than or equal to 3n by 4. This is what we just saw. And what that means is that this both of these are sub-instances of size at most. These are at most t of 3n by 4. Okay, and we go into only one of these, right? So we don't go into both of them. Therefore, you get a running time of t of n is less than or equal to O of n plus f of n plus t of 3n by 4. Okay, so this is what you have. Okay, so imagine for a moment that f of n can be done in time O of n, right? Which is you can find an almost median, which is a somewhat easier problem, right? It's like saying that, oh, find me some element that's roughly in the middle. Imagine that you can do this in time of n. Okay, then what you would get is a recurrence of the form t of n is less than or equal to O of n plus t of 3n by 4. Okay. And let's, for concreteness, let's just write it as c times n plus t of 3n by 4. Okay. Now what does this recurrence solve to? So you can use a simple plug-in check kind of a method. So this would be cn plus c times 3n by 4 plus c. So let me write out one extra step and then I will simplify it. So t of uh, 3 by 4 squared n. Okay. And now I again expand it out and keep going. So what I would get is Cn times 1 plus 3/4 plus 3/4 whole square plus so on. Okay. Now, even if you had an infinite series like this would only add up to a constant. Okay, so this is a simple exercise for you. This is a geometric series with decreasing terms, so it converges to a constant. Okay, so it converges to a constant. So overall, you have that this is equal to O of n. Okay. So if you somehow had an approximate median finding oracle that works in time O of n, then overall you get a running time O of n. Okay. So the next two, I'll stop this video now, and the next two chunks of the video are going to talk about how to find an approximate median. And so I'll give two things. One is a randomized algorithm that actually has this kind of a behavior. And the next is a clever deterministic algorithm, which is not quite this, but which is not so direct. It itself has a recurrence. And we'll see how to analyze that. Okay, so I will do that in the next couple of videos.